Hello everyone, welcome to AP Chemistry 2024 free response problem number 1. This problem is dealing with acid-base neutralization reaction, and we have a lactic acid. This weak acid is titrated with sodium hydroxide, strong base. So this one is very typical situation of acid-base titration. As a result, we are forming water and salt. Sodium lactate is formed. Now, student learning objective for this problem is threefold. First, we need to understand solution stoichiometry. So, lactic acid is a monopropylic acid. Sodium hydroxide is also one hydroxide in the formula. So this one, as you see in this balanced equation, it is one-to-one reaction. We need to be able to calculate the concentration of sodium hydroxide ion. So as in number 1b, it is asking us to calculate the concentration, and also we need to look at the Lewis structure, bond line formula, figure out which one is the most acidic hydrogen. So we'll be going into a little bit of organic chemistry. So I'll be explaining with the concept of terminologies of organic chemistry to make it clearly present to you. Second step, acid-base reaction is very clear reaction. By our naked eyes, we cannot see the progress of the chemical reaction. The only evidence we have is the test tube or the reaction. The glassware becomes warm. So this is an exothermic reaction. Heat is generated. We'll be calculating in problem E. It is giving us a quantitative data to calculate the exothermic. So it is this one, delta H is always a negative value, giving out heat to the surroundings. Number 3, this one is more general. This is very repeated pattern of like asking students' understanding of this acid-base reaction. First, titration curve. When titration curve is given, x-axis is now volume of the base, y-axis is now pH. So initially, the solution is acidic solution, lactic acid dissolved. As you add more and more of sodium hydroxide from the burette to the olegmine flask, the pH will be going up. At equivalence point, close to the equivalence point, the pH is jumping up and becoming a very basic solution as it passes through the equivalence point. So we need to know what is the concept of equivalence point. Equivalence point meaning the mole number of the acid becomes equal to mole number of sodium hydroxide. So it is completely neutralized. That's the concept of equivalence point. And half of the volume of the equivalence point volume, that is called half equivalence point. And the significance of half equivalence point is that in this type of titration of a weak acid with a strong base, the pH value at the half equivalence point is equal to the pKa value. This one can be calculated by the Henderson-Hasselbalch equation. This is a buffered Henderson-Hasselbalch equation is only applied to a buffer solution, and along, close to, in the vicinity of the half equivalence point, the solution becoming buffered solution. So these three objectives are asked to students very often, and so we need to understand this one clearly. Now let's look at the problem A. So this is lactic acid. Lactic acid is 3 carbon compounds. Methyl group here in the middle carbon has hydroxyl group OH, and at the end we have a carboxylic acid. Those functional groups, we call this one functional groups. Let me highlight it. So hydroxyl group, this one is alcohol. Any carbon compound that contains hydroxyl group we call alcohol. This is alcohol, and more important than that is at the end we have carboxylic acid. We need to understand carboxylic acid very well in nature, in biochemistry and organic chemistry, and many of the bio compound and natural compound contains the carboxylic acid group COOH. And we need to understand about the carboxylic acid, that is a weak acid. So in water, in aqueous solution, carboxylic acid, all the carboxylic acid is functioning as a weak acid. And hydroxyl group This is also very weak acid, but water is a little bit stronger than hydroxyl group in its acidity. So in water, hydroxyl group doesn't function as an acid at all. And why carboxylic acid is weak acid? We need to look at from the viewpoint of two things. First, the oxygen is much more electronegative than hydrogen. So oxygen is partial negative, hydrogen carrying partial positive. So when strong base is coming in, taking proton away, hydrogen away, so we see it is relatively easily taking proton away. And third, when you look at the conjugate base, let me look at this group as an alkyl group. Let me write this R, RCOOH. So when base is coming in and taking this hydrogen away, it will be forming conjugate base. The conjugate base is carboxylate ion, 3 negative charge right there, and then we have a BH. Okay, so this one has a resonance structure. We can draw resonance structure. The negative charge is spread out, delocalized between these two oxygen atoms like this way. So this resonance structure, resonance stabilization, the delocalization of negative charge is really spreading out the negative charge and stabilizing the conjugate base. In this way, because the conjugate base is stabilized, there is more trend or more, we call this one spontaneity to this acid becoming deprotonated. That's why the carboxylic acid, the hydrogen at the carboxylic acid is now a weakly acidic. All the other hydrogens are not acidic at all in aqueous solution. In organic solution, the hydroxyl group is also becoming deprotonated, but in general chemistry, in this AP chemistry level, we are studying about aqueous solutions. So just assume only carboxylic acid, the hydrogens are acidic. Okay, now let's move up to quantitative aspect of this reaction. We have dissolved 10.22 grams of sodium hydroxide in an aqueous solution, making final solution volume 500 milliliters. And then we need to calculate the molarity. So this is very usual situation. Sodium hydroxide is a pellet, white pellet. This is not powder and not a granule. So then we need to quickly measure out 10.22 grams. This is hygroscopic. Sodium hydroxide is now receiving moisture, becoming, a little bit of absorbing moisture. So then we need to be quickly measuring out and dissolving into water. All right. So molarity is defined like this way: per unit volume, per 1 liter. Usually unit volume is 1 milliliters. We are using many times, but for molarity, 1 milliliter is too small in our calculation. So unit volume should be liter. Per 1 liter of solution, how many moles of solute is dissolved? That's the definition of molarity. So then let's calculate. We need to calculate mole number, volume independently and put them together. Calculate the molarity. Okay, so we are ready. Let's get started. So unit conversion is very important in general chemistry, AP chemistry. 10.22 grams of sodium hydroxide. We want to convert this one into a mole number. In order to do that, we need to write grams of sodium hydroxide at the denominator and moles of sodium hydroxide at the top, because we want to cancel out the grams of sodium hydroxide. We want to convert it to the mole number. And the value must be equivalent to each other. So 1 mole. From the molarity, we know that 1 mole of sodium hydroxide has 40 grams of mass. And do not lose the zeros, trailing zero that's fixed here. And when you plug in this one into the calculator, I already calculated this one. It is 0.2555 mole of sodium hydroxide. Okay, so this one has 4 sig peaks, and this number also 4 sig peaks, and 1 is the definition, infinite number sig peak there. So we need to write at least 4 sig peaks. And think about the volume. This is 500 ml. So let's convert 500 ml into liter. So mil down and liter top. 1 liter is 1000 ml by definition of this number prefixes. So this is 0.500 liters. Okay, so when I teach this class in college, like general chemistry, preparatory chemistry, I see students often don't care about writing the trailing zeros, but please write the trailing zeros, because here I see the author of this exam put intentionally the decimal point there, signifying that the trailing zeros are suffix. So we need to write definitely trailing zeros there. So keep 3 suffix. Okay, finally let's put into a equation. Molarity calculated by mole number of the solute and normalized by the volume. So let's plug in 0.2555 moles of sodium hydroxide, and it is dissolved in 500 milliliters, which is 0.500 liters. And let's calculate is 0.511 moles per liter, which is molarity. So then we are able to calculate this one. Sodium hydroxide is 0.511 molarity. Please have an idea, working concentration is usually less than 1 molarity. When it is more than 1 molarity, it is highly concentrated. So then usual working concentration now 0.2, 0.3, 0.456 molarity in this range. Okay, so we feel good. Now let's move up to the titration data. So after the titration, we were able to construct a titration curve. The titration of 25 ml lactic solution is now like this way. Okay, so we need to first identify the equivalence point. Please note that the equivalence point is where the pH is now abruptly increasing from low to high. So then middle of this value around here, that's equivalence point. Okay, here when we go to find the pH value, the pH at the equivalence point is approximately 8 something. This is bigger than 7.0. Oh, interesting. At equivalence point, pH must be becoming 0. No, in this case, we have now completely titrated an acid. Now, acid is 100% converted into its conjugate base. And conjugate base of a weak acid is weak base. Because we have now weak base, the pH of the solution is now slightly basic. Okay, more important than that is we need to recognize the half equivalence point. First, let's recognize what is the volume. So in my drawing, it is a little bit off, but in our computer graph, generated graph in our AP exam, you see that the equivalence point is exactly falling on 16.0 milliliters. Then half is 8.0 milliliters right there. And let's bring it up. Let's bring it up. Where it is intersecting with the pH curve, and it is right there. And the pH value right there, this is pH value at half equivalence point. Here pH value is becoming equal to pKa according to the Henderson-Hasselbalch equation. Okay, and then around this half equivalence point, so this one is half equivalence point, and the pH is now increasing. The slope is very small. We call this one here, this region, this is called a buffered region. So the solution became buffered. Initially we had weak acid only. When you add a strong base, sodium hydroxide, then it is titrating. It is neutralizing the weak acid a little bit, so it is forming conjugate base more and more. So around this half equivalence point, at the half equivalence point, now half the amount of the weak acid is converted to weak base. So it is the equimolar, but around it. So when amount of weak acid conjugate base, they are comparably present, we call this a buffer solution. So then around this, the half equivalence point, it is buffered region, so we can apply the buffer equation, which is Henderson-Hasselbalch equation. All right. So determine the pK value. pK value from the half equivalent point is about 3.8. Because the y-axis, it is increased by 1, pH is increased by 1, and so we can only having first decimal of pH value. We cannot have 3.8 to 3.7 something, because 3.8 is already estimated value. This one is uncertain. Somebody may read it, this one is 3.7. So do not go into all the way to second decimal. Let's stop at first decimal. Okay, now let's move up. Now, at certain situation, the snapshot of the solution shows like this way. We have sodium ion is spectate ion, so we don't need to think about sodium ion. Now, the lactic acid is conjugate base lactate ion is present like this way. Out of 6 particles, 4 particles are HA, and 2 particles are its conjugate base. Okay, like this one. All right. So then find draw X on the preceding titration curve at a point, titration where the reaction mixture would be represented by the diagram. So here out of total 6, initially it was all like lactic acid. Out of 6, we have now, so only 4 of them, initially 6, 4 of them remaining, and or out of 6, let me think about it, 6, 2 converted into a conjugate base. So then this is 1/3 of the volume of the equivalence point. So then here 16, 1/3 is 5.3. So then about 5.3 here, this one will be our X. Or as you see here, this is belonging to the buffer region, very close to the half-equivalence point, so we can apply the Hasselbalch equation now. pH is calculated by a constant, pKa is a fixed value constant plus logarithmic value of the weak acid concentration under conjugate base concentration. So then we know that HA over, A negative conjugate base over HA, we have 2, and over 4, this is half. And we figured out pK value is 3.8. 3.8 plus log of 1/2, then we find that this value is 3.5. Okay, so then when you go to 3.5 right there, go right there, then we are also encountering this point. So this way it is confirming that is what is asked in this problem. Okay, next one, let's move up. Now, experiment was repeated with 2x concentration of sodium hydroxide. Initially, in experiment set 1, 10.22 grams of sodium hydroxide dissolved in 500 milliliters solution. Now, double the amount, 20.544 grams of sodium hydroxide dissolved in 500 milliliters solution. So let's draw the titration curve. Here again, the concentration 10.22 we already calculated. The concentration of this solution is 0.511 molarity. So in the second case, this is the volume is the same, only the amount of the sodium hydroxide doubled. So then this concentration of 5.11 times twice, which is 1.022 molarity. Okay, let me underline the sigfix. The first 2 is less significant, but let's keep all the numbers to minimize rounding error. Okay, so then how can we calculate the equivalence point? All right, in 0.511 molarity of sodium hydroxide, the equivalence point is 6.0 milliliters. Then what about 1.022 molarity? What would be the volume of equivalence point? Okay, so the equivalence point, this one is now 16.0 mil. Let's divide both sides by 1.22, then it is 0.511 molarity or over 1.022 molarity, which is half of it, half milliliters. Okay, so then at half here, it will become a equivalence point. Here, the pH will be 8 point something. We need to bring it up. We need to follow this order, and then going close to the equivalence point, it is shooting up and follow like this order. So this will be, the green line will be new pH curve. Okay, now let's move up to E. Now, in this SMS neutralization reaction, we are given equimolar amount of HA and NaOH, both of them 100 milliliters and 0.5 molarity of concentration. And when you mix them together, when you measure and monitor the temperature, you find that Temperature initially 20 degrees C, when increased to 23 degrees C. Specific heat of the solution is 4.2 joules per gram Celsius. So specific heat of water, pure water, is 4.184 joules per gram Celsius. So this one is similar, and then density is 1.00 grams per mil. This is the density of water for a solution. Usually density is slightly higher, like 1.03, 1.04 grams per milliliters, but for this exam purpose, so the authors of this exam wanted to simplify the situation, so give the density of water. Okay, so then how can we calculate amount of heat? Think about heat equation. Amount of heat is now mass of the material times specific heat times change in temperature delta T. Here mass is, we need to calculate the mass. Mass is 200 milliliters. The volume is now additive. We are mixing up 100 ml, 100 ml, 200 ml times the density of solution is 1. So it is 1.00 grams gram per mil. So it is 200 grams. Mass is 200 grams. C is given 4.2 joules per gram Celsius. And delta T is 23. 0, final temperature minus initial 20. So then the temperature increased by 3 degrees C, like this way. Okay, we are ready. Just plug in to this expression. So then Q is equal to, Q amount of heat in joule quantity is equal to 200 grams. 200 grams multiplied by 4.2 joules per gram Celsius. So when you have 1 gram of the solution, to increase the temperature by 1 degree C, we need to apply 4.2 joules of heat, and temperature difference is 3.0 degrees C. Okay, so we'll see everything will cancel out. Grams divided by grams cancelling out, degrees C cancelling out. We have now finally joules. That's good. That's the unit of energy, unit of heat. And when you calculate this one, this is 2,688 joules. 200 has 3 suffix, and 4.2 has 2 suffix, and 2 suffix. So let's represent with the 2 suffix. So 2 and 6, and from 8, let's round up. So this one, 2,700 joules. That will be our final answer. Here, as always, before we write the final answer, let's stop to think for 10 seconds about the suffix. When multiplication or division, we are taking the smallest number of suffix, the fewest number of suffix. Okay, now next number. Now calculate the molar enthalpy. So here, mole of acid, mole of base, both of them same, equimolar. It is 100 milliliters times, let's convert 100 milliliters to liters, and times molarity. It is 0.5 molarity, 0.5 mole per liter. So this is now 0.0500 mole. So then molar enthalpy is mole number normalized by the volume. So here let me erase it. So molar enthalpy is now amount of heat normalized by volume of the limiting reactant. In this case, they are stoichiometric. There is no limiting reactant. Both of them, the mole number same. So 2,700 joules over 0.05 mole of quantity. So this one is 2 suffix, 2,700, 0.0503 suffix. Let's represent with the 2 suffix. It is 54,000 joules per mole. And let's convert this one to kilojoules. 1 kilojoules is 10,000 joules. So this is finally 54 kilojoules per mole. Okay. So here I wrote this one as a positive number, but molar enthalpy is actually negative because this one is exothermic reaction. Acid-base reaction. As a result of acid-base reaction, the solution temperature went up. So then from the reaction, that's the system, it gave out the heat to the surroundings, which is the solution, and solution temperature went up. So delta H, when you write it, final answer, let's write it negative number. And finally, number 3. The student claims that if heat is lost from the calorimeter to the surroundings, so usually this one we are using calorimeter cup, and it is inevitable to lose certain amount, a small amount of heat to to the air. So this is what the student, some student says. Then the experimental value of the molar enthalpy of the reaction will be smaller in magnitude than the actual value. Do you agree or disagree? Okay. So then when we lose, okay, so here total amount of heat generated, but this one measured value, measured, and also some of them will be lost to the surroundings, to the air. So then this one is positive, some certain value lost. Anyway, so Q actual, this is actual, and measured value, Q measured value is smaller in magnitude, smaller than actual. So then delta T will be smaller, and Q smaller as a result, delta H will be smaller. So agree. It will not make a very large difference, but many times significantly enough. Or we need to use tightly sealed a coffee cup calorimeter to minimize this loss of heat. Anyway, so Q will be a little bit decreasing. So in this, I'm going to conclude now this coverage of free response section, free response question. Let me recap what we have learned in this part. So this one is very typical reaction. So please go over this problem thoroughly in your own time. So this is containing multiple concepts. First, do you understand acidity from the Lewis structure, from the bond line formula? We know which one is most acidic proton. And can you calculate the molarity? And do you understand titration curve and the concept of half-equivalence point? And to understand also the stoichiometry and also heat equation, Q equals MCAT, Q equals MCAT, and then applying into the mole number. Molar. So enthalpy, the kilojoules per mole, conversion between joules to kilojoules, and then divided by, normalized by the mole number to find the value. So this is very multifaceted problem, and this one is very important problem in general chemistry, AP chemistry. So please take time to have a thorough review of this problem. I'll be coming back to another video of acid-based problem. Thank you. I'll see you in later.